Okay, let's take a look at a couple of convolution examples using a technique known as graphical convolution. It's actually just a method to help you determine the limits on the convolution integral. So the first example we'll look at is convolving a unit step. So u of t with a function h of t that's equal to a switched exponential e to the minus t u of t. So again, you can think of this as the response of a circuit, in this case an RC circuit, that has this impulse response, and we'll calculate the output in response to a unit step. And of course, in response to an impulse located at t equals 0, this is what we'd see. We'd see h of t. And if the impulse were at a different location, we'd see a shifted impulse. But we want to find the output due to this particular input. And so from our convolution integral, we have y of t is equal to integral from minus infinity to infinity of x of tau h of t minus tau d tau, or we can calculate the output by integrating h of tau x of t minus tau with respect to tau. And so either of these will give you the same result. In the integrand, the first term here, x of tau, or h of tau over here, is just the normal function. And the second term, either h of t minus tau or x of t minus tau, is a time reversed and shifted version of the original function. So what I recommend is that you time reverse the simplest function. So in this case, it's x of t. That's a little bit simpler than h of t. Again, you'll get the correct result if you time reverse either of the two functions. So I want to use this formula that involves the time shifted x of t function. So I want to get an idea of what that looks like. And again, keep in mind that we're integrating with respect to tau. So first I want to draw x of tau. Again, that's a simple substitution. I just substitute tau for t here, and so in this case that's u of tau, and as a function of tau, and that's just our unit step. Okay, and x of minus tau, then the time reversed version of that function, would look like this. Okay, it's 0 for all tau greater than 0. Okay, so this is x of minus tau, and that's equal to u of minus tau. And then finally, I want to sketch x of t minus tau, and that would be equal to u of t minus tau. That's a shifted version of the time reverse function where the origin is shifted to t. So typically we start off with, in this first picture I'll show t as being negative. This is a function of tau. And then, so if I plug in t equal to tau here, I'll get, or when tau is equal to t, I'll get u of 0, which is at the origin. And then for all t greater than tau, back in this portion of the curve, I'll have a positive argument here, and so that's equal to 1. And then for all tau greater than t, this will be negative, and then so u of that argument would actually be 0. So the trick in evaluating this convolution integral, notice that the output is actually a function of t. So I've got to figure out what this integral is as t changes. In other words, as this thing shifts across here. Again, typically we'll take look at this as t goes from minus infinity all the way to plus infinity. So as this thing moves across here, I have to evaluate the integral for different positions of this time reverse function. Okay. H of t, or rather h of tau, is the other term in this integrand, and in this case h of tau is just going to be e to the minus tau u of tau. So that would look like this. And it's a function of tau. This is 0. It's equal to 1. So this is a sketch of h of tau. And in this particular case, I just substitute tau for t. I get e to the minus tau u of tau. And what I have to look at is actually I'm integrating over the product of these two functions, the one here in the lower left and this h of tau function, for different versions of t. And I can see that as long as t is less than 0, then the product of these is going to be 0 everywhere, because this function is 0 for all tau negative. This function is 0 for all tau greater than t. So as long as t is less than 0, the product is going to be 0, and y of t would be 0. So that's one case, or one region. So for t less than 0, I have the result that the output is 0. And physically this makes sense, because our input, our original input, doesn't arrive or start until t equals 0. So we don't expect any output in this case, because it's a causal system, until t is equal to or greater than 0. Again, you can use that convolution property where we add the start times. Here the impulse response starts at 0, our input starts at 0, so we don't expect the output until t is equal to 0. Okay, now I want to sketch what this looks like. Let me go to a new board here. Again, I'll sketch h of tau. It's e to the minus tau u of tau as a function of tau. Again, it looks like this. This decaying exponential. And then I'm going to sketch x of t minus tau, but now for a case where t is positive. So this is the time reversed function, so the origin is shifted to t. Okay. Then now if I look at the product of this function with the one above it, this function is equal to 1 between 0 and t, and then h of tau is 0 for all tau less than 0. Of course, this function is 0 for all tau greater than t. So this is actually just going to, in the product, I'm only going to see that exponential in this region between 0 and t, for tau between 0 and t. And since this this function is equal to 1 in that interval, this function is equal to e to the minus tau u of tau. What I see in the product is e to the minus tau u of tau. So that's what this portion of that integrand looks like. The next step is actually just integrating this, finding the area under the curve, and that gives me, in this case, my limits on my integral are between 0 and t. That's the only region where this is non-zero, and I'm integrating e to the minus tau. U of tau is 1 in this region because I'm considering the case where t is greater than 0, and so in this interval tau is between 0 and t, so that just becomes d tau. I can carry out that integral. I'll get minus e to the minus tau evaluated at 0 and t, or minus e to the minus t minus evaluating this at tau equal to 0, e to the 0 is 1. I can rewrite this as 1 minus e to the minus t. Again, this result is valid only for t greater than 0 and applies for all t greater than 0. So I can write the final result for y of t as this form. It's equal to 0 for all t less than 0, and it's equal to 1 minus e to the minus t for all t actually greater than or equal to 0. If I evaluate this at t equal to 0, I see this term is 0 as well. So if I sketch this, I see that I get a continuous output for y of t. It's 0 here at the origin, and then it's equal to 1 minus e to the minus t here. As t becomes larger, this term goes to 0, and this thing approaches 1. So this is what the output would look like. Remember, in response to an impulse, the system just gave me a decaying exponential. This is the response to a unit step. So sometimes this is called the unit step response. Another way to actually write this is to take advantage of my switching function and use the unit step as a switching function, and I can write a little more concisely in this case that y of t is 1 minus e to the minus t. Of course, it's only equal to this for t greater than 0. So this is another way to express the output of this particular system. Either of these two forms is acceptable. Again, note that the starting time of my input was at 0. The impulse response also started at 0. So the starting time of the output is at 0. In this particular case, too, both these functions are really infinite in duration, so I expect the width of the output to also be infinite.